Hello, everyone. That went a little quick. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I'm very happy to have Dongwook Lim with us today. Hello, Dongwook.
Hello, Frank, and hello, everyone.
And where are you located at? What's your geolocation, Dongwook?
So actually, I am living in Seoul, in Korea. So and I'm working with the Yonsei University, which is one of the biggest the university in Korea, which having a department of astronomy. And here, this room is our common room of our department.
Very cool. Korea, does there get snow on the ground? Do you have snow?
Yes, right. So actually, last weekend I saw that the winter is over and spring is coming, but it was my illusion. From yesterday, it's snowing outside from yesterday, and the temperature is drop again. So Korean winter is not that easy.
Winter is back. Winter is back.
Yeah, it is back.
Yeah, on this, well, my February 5th, it's your February 6th, 2024 as we record this. Yeah, and winter came back a little bit in Phoenix as well. So we're getting another dose of rain here in a couple of days that's coming over from California. So not quite spring yet here either. So we're getting there. Cool.
Yeah, we should more time for waiting spring.
Waiting. Cool. And Dongwook, what do you like to do for research?
So my research, so actually I'm interested in the many kind of the star in the Milky Way. So actually I begin my research from the global clusters. And from that, so I am now interested in the stars in the galactic bulge and halos and some kind of the special, so interesting objects such as white binaries or the variable stars and many things. So actually I want to study many kind of the interior stars in the Milky Way. So
cool.
That's what I want to.
Very cool. Very nice. And that is going to bring us to maybe not so peculiar ones. Let's see. And we're going to bring this up. And this one is an AJ article. You'll notice there's color coding. We're doing an experiment on people. So it is the open access era. You can go grab a copy of this article for free. So go get one. Chemical homogeneity of wide binary systems, an approach from near-infrared spectroscopy. And Dongwook, take us away.
Yeah, thank you. So as Frank said, the title is Chemical Homogeneity of the Wide Binary. So I make some highlight in the paper. Actually, in this article, so we have two main aspects, two main point of view. The first one is for the wide binary system, and the second one is for the near-infrared spectroscopy. So in this article, the yellow highlight is for the wide binary, and the green one is for the near-infrared spectroscopy. So I make some highlight for your convenience. So in this, when I'm reviewing these papers, I'm gonna show you so what is the wide binary and what is the power and the usefulness of the near-infrared spectroscopy. Okay, so just before the beginning, reviewing this paper, I want to introduce my co-authors. The first author is Dongwook Lim, it's me. And the second author is Andreas Koch Hansen. He is working in the Heidelberg University in Germany. He's my former postdoc supervisor. And he's a real expert in many stellar astronomy, in the galactic stellar astronomy. And he's the man who first introduced me about the wide binary system. So,
nice. Good show.
And the other author is Seung-Soo Hong. He is a postdoc at Seoul National University in other university in Korea. And his research is on the stellar population in global clusters and the galactic bulge. He was the real actual PI of this observation. And the next author is Sang-Hyun Chun, Dr. Sang-Hyun Chun. He is working on the Kashi, and he's an observing specialist, especially for the near-infrared photometry and spectroscopy. And last author is Young-Wook. He is my the PhD supervisor, and currently working with me. And his research topic is really wide, from the RR radar and the horizontal branch star to the supernovae cosmology. So, and I would like to say thanks again for this co-authors.
Great shout out.
Yeah. Okay. Let's move on to the article. So yes, the first keyword is wide binary. I think some of you are not familiar with this word, wide binary, but it's just a simple word. This wide binary is just one kind of the binary system, but this binary has a very wide separation between two component stars from a few AU to more than 1,000 AU. Sometimes the separation is almost 1 parsec, more than parsec. So in order to study this wide binary system, we have performed the high resolution near-infrared spectroscopy using the iGRIS instrument. So in this paper, I'm gonna show you some chemical properties of the wide binary and why this high resolution near-infrared spectroscopy is necessary and what is the power advantage of this spectroscopic observation.
Cool.
Good. So, okay, let's move on to the introduction part. So there is a very important point. So why we study this wide binary system. So wide binary system is quite common now. So, you know, after Gaia data release, the galactic in the Milky Way stellar astronomy has dramatically changed after Gaia data release because the Gaia probably provides the very accurate proportion and there's astrometric structure for number of stars in the Milky Way. That it was great. So in case of the wide binary study, the known number of the wide binary is hugely increases after Gaia data release. Here, as you can see, so around 20 years ago, there is only 1,000 wide binaries reported, but now there are more than 1,000, more than 10,000, or more than about a million wide binaries newly reported, but that is still candidate. We need to check that. So this is why studying the wide binaries become more important after Gaia data release.
Very good.
Yeah. If I add some sentence for the wide binary, this wide binary itself is very peculiar object because this wide separation between two component stars is not easily made from the single collapsing cloud because the separation, the size is much larger than the single star-forming cloud. And so, and also their low binding energy is also a problem. So surviving of the wide binary is still challenging. So in spite of their low binding energy. So there are some scenarios for the formation of the wide binary. So they beautifully explain the formation and evolution of the wide binary, but we don't know yet which one is the origin of this wide binary system.
Or many channels.
Yeah, right. So, and also, this wide binary system, so their formation and evolution itself is a problem, but the more important thing is we can use this wide binary for many kind of the astronomical aspects. So in the second column, you can see the red highlight. So because of their peculiar property, so the low binding energies and the similar chemical properties between the component stars, this can be used served as a variable tools for many things. So for example, so it can make the mass constraint of the macho system. It's one of the dark matter. And also it also used for checking the chemical tagging technique and the spectroscopy, checking the calibration of the spectroscopy data. And this can also be used for studying the accreted dwarf galaxy, such as Gaia and Enceladus, Sapphires, and other things. And the one more interesting we can do with the wide binary is to study the star to exoplanet interaction. So I'm gonna show you some example at the later about this. Okay. Yes. Next is the green highlight for the spectroscopy. So you know, so in stellar chemistry, the spectroscopy is very useful tool to study their chemical abundances and their stellar properties. Especially for the near-infrared spectroscopy is a little bit new technique compared to the optical spectroscopy. And then so far, so many stellar properties is studied with optical region, but here in these days, the near-infrared can be used for more studies. Actually, this high resolution near-infrared spectroscopy has some advantage compared to the optical band. The first one is they can obtain the high quality data for cool star because cool star is brighter in the near-infrared region than the optical. And the second advantage is it can observe the stars or targets in the highly obscured region, high reddening region. For example, the galactic purge. This is one other advantage. And also, in this near-infrared observation can measure the precise measurement, can measure the precise abundances of the volatile elements and molecules, which means the carbon, nitrogen, oxygen, and so on. That is the main source of the exoplanet, gas giant planet. So it is already, this near-infrared spectroscopy is already used for the studying the atmosphere of the exoplanet.
Yes.
It's time to study the exoplanet. So this is why we're focusing on the high resolution near-infrared spectroscopy in this article. So, okay, that's good. So that's my introduction. So why we study wide binary, especially using the near-infrared high resolution spectroscopy.
Cool, nice. I'm with you.
Yep. Okay. So next is for the observation and data reduction part. So our observation was made during the two observing years. First one is 2021B and second one is 2023A semesters. Actually, these two observing years has a little different purpose. So at the first run, the 2021. So we are more focusing on the wide binary system with wider separation, the typically larger than the 10,000 AU separation.
Okay.
And also we are focusing on the near-infrared, the power and the validity of the near-infrared spectroscopy. So that is a general purpose, our general purpose at the semester. So at that time, we use the catalog of the Jimenez Estebanador 2019 catalog. Okay. But for the next semester, 2023A observing year, we focusing on some kind of peculiar wide binary, which suspected to have an accreted origin. So which means that they are associated, they are formed in the outside of the Milky Way and then accreted in the Milky Way. So which is part of the Gaia and Enceladus versus acquired event. So at this time, so we're using the different catalog to select either more accreted stars, which is a super wide catalog. Yeah. Super wide. Yeah, next one. Yeah, super wide question, because this catalog included many high performance data.
Yes.
Okay. So from this catalog, we selected some stars. So from the orbital energy, angular momentum and orbital energy. And finally, we selected some 8 comorbid pairs, so comorbid candidate, so which we expected that is related to the other some accretion event.
Okay.
Yeah. Actually, so we got some observing time for many wide binaries, but due to the telescope schedule and the weather in the Chile, so during that the weather condition was not that good, so we can only obtain the 10 and 1 comorbid pairs in this each semesters. So yeah,
good start. We'll come back to that. We'll come back to that.
That is enough number.
Yeah, we'll come back to that. Okay, very good.
Yeah, for this observation, we're using the IGOS instrument at the Gemini South Telescope. IGOS is very powerful and interesting instrument, and this is a high resolution near-infrared spectrograph, and which have the 2 spectrographic arms covering the H-band and K-band regions simultaneously, and the spectral resolution is around 45,000. This is one of the powerful spectrography in the near-infrared region. So we got that observing time through the KGMT science program. So that is the Korean KASI and the Gemini Institution. Is a part of the Korean KASI and the Gemini Observatory Association program.
Yes.
So, okay, as I said, we observed 10 and 1 wide binary pair from each observing runs. But yeah, so it's time to go to that purple highlight. The purple means there's some kind of the challenging and problem of this article. Okay. So it's time to admit my mistake, our mistake. So actually, we observed 10 pairs, but we cannot use all of that. So out of 20 stars, so the 10 pairs, but we can only measure the chemical abundances and spectroscopic analysis only for the 11 of them.
Okay.
That is because of their weak observation features in the near infrared region because of, due to their high temperature.
Okay.
So this is very basic knowledge that
We'll come
so
back.
when we selected the target stars, we only consider their magnitude in the near infrared region, but we should consider the temperatures and the color of that because the higher temperature stars there is a black body radiation. Their plane cover is dropped down at the near infrared region. So even though their magnitude is bright enough, but their observation feature is moved away, removed. So would you move on to the figure 1?
Hey.
Yeah.
Still? Gotcha.
Yes, here. Yeah, this is the color magnitude diagram. So our target star, the color coded is our target stars, which were able to measure the chemical abundances. But the problem is the open symbols. So open symbol stars, we observe these stars, but we can't make any kind of the spectroscopic analysis because of the high temperatures.
Right.
So yeah, here's in the magenta line, vertical magenta line, the divided stars, which we can make the spectroscopic analysis or not. So that was our fault in the target selection process. But I want the other observer, astronomer, do not make the same mistake. So please consider their color and temperatures when you want to observe some high temperature stars from the near infrared region. So we make some constraints on the Gaia BP minus RP colors and the 2-match J minus K colors. So that's all. So finally, among 11 wide binary pairs, we can use 6 wide binary pair system.
Okay, whittling down.
Yeah, okay, so would you move?
I'm with you.
Yeah, so would you move the slightly lower?
Okay, let's go down to the article, data reduction, target information.
The further time of the data reduction and later, yes, stop in these tables. Okay. The first step of the spectroscopic analysis is measuring the radial velocity. So we observed wide binary candidate. Why I say that is candidates because they are selected only based on the proper motion. So from the Gaia. So we don't know yet about the radial velocity information. So if that is really co-moving stars in the 3D space, we need to check the radial velocity of that stars. And if they have the the proper motion and also radial velocity. So this means that they are co-moving in the 3D spaces. Here, this table 1 is a target information obtained from Gaia DR3 of the observed star. Or yeah, you can see their proper motion here, and the 2 component stars, the 2 stars, 2 component stars of each wide binary have very similar radial proper motion values. And the first 5 wide binary pair, 10 stars, is from the first observing run, and the last one, SWB 111893 A and B, is observing Sergeant A observing runs. Okay, but here there is no radial velocity information. So, but that is released by Gaia DR3. So actually, when we propose the observation and make the observation of these stars, there was no information of the radial velocity. But after that, Gaia provides this information.
Yay! Okay.
But it's good. It's quite good.
Very
so
good.
and see here, the 2 component stars has very similar radial velocity. The difference is around 1 kilometer per second. This means that they are real wide binary system within the 3D. But the problem is the last one. So Gaia provided only the radial velocity only for the component B stars, that is minus 191.
Okay.
Yeah. So for this wide binary system, we need to check that radial velocity is layer. So yeah,
a little bit larger.
So would you move on to the next table? So in the next page.
Okay.
Yeah, table 2.
Table two. Let's go to table two. Table two.
Yeah, here. This is the ladder versus what we measured from the eigenstate data. And as you can see, for the first five pairs of the wide binary, the ladder velocity is quite similar with that obtained from the Gaia. The difference is around 1 or 2 km/s, and we can also confirm that the ladder velocity difference between two components in star is less than 1 km/s. Yeah. This is a strong evidence that this wide binary candidate is not just randomly co-moving, just have random common proportion. That is the real co-moving star. But the problem is the last one, SWYB 11893. We obtained we obtained quite different radial velocity for this star. Minus 189 and minus 58. This means that the radial velocity is quite different and they move in different way. This means that there is not clear wide binary system. And also when you compare to the Gaia DR3 radial velocity, that is also different. The actual which go back to the table one. So
right. Yeah, minus 191.
Yeah, in Gaia DR3, there's minus 191 for component B star, but this similar value is obtained for component A star. Yeah. I think that is because I think that is because these two stars is too close. Their angular separation is only 5 microseconds. So it could make some kind of there's a confusion. So
let's go back
to the Gaia data.
Okay.
Yeah. So actually,
but a little even under 5. Okay.
So anyway, so in this region, because of this large difference in radial velocities, we excluded this target from our analysis in this article. So this is very unfortunately, this is only one target observed in the 2028 semester. So for the studying accretion origin. So we cannot make that kind of study at this time. We just keep this study in the table for the next time.
Correct. Good.
So in this article, we only focused on the general property of the wide binary with wide separation and the power of the linear and practice spectroscopy.
Yes.
So finally, we have 5 wide binary pairs. Okay. So would you move up?
Oh, sorry.
Previous page.
Previous page, yes. Oh, there we go.
Here, this page. Okay. Now, so next step is to determine the atmosphere parameters. So if we want to measure the chemical abundances of stars, we need to determine the atmosphere parameter, effective temperature, surface gravity, and microturbulence velocity. So in usual optical spectroscopy, we can obtain these parameters from the spectroscopy way. So for example, the ionization of between the local ionization between the iron 1 and iron 2 line, and to reduce the trend between the abundances and the equivalent width. But in case of the near-infrared spectroscopy, it's not easy because we don't have enough iron trine in this region, and there are very severe blending by the molecular band. So in our previous study using the eigenstate data, we're using some kind of the alternative method, so which is the line depth relation method or the equivalent width of the CO method.
Okay.
So, but at this time, we cannot use that method too because of the relatively high temperatures of our target stars.
Okay.
Yeah, so we cannot check the line depth and the CO band from our stars. So instead of that, we using that blue part. Instead of that, we using the photometric temperatures. So we measure the photometric temperatures from the J-K color.
Yeah. Okay.
Yeah. So I want to mention that at this time, we're using the 5 kind of the reading value in the next highlight. So we use the Schrager, so Schaffler and Binker map, best 17 and 19 map, and also Stelizio. It is very, you can have the question, why you using this 5 kind of the reading map? So I'm going to show you why we have to use this 5 version of the reading map.
Okay, I'm looking forward to that. Good.
Yeah, right. Yeah. After the measurement of the temperature, we also measure the gravity and the micro temperatures using some kind of canonical and empirical relation. And finally, we compare the atmosphere parameters for this white binary pair. In the right panel, you can see the red block. So from when you see this stellar atmosphere parameter, we can see that we can find the very similarity in all atmospheric parameters between the two component stars. The difference in temperature is less than 200 Kelvin, and the gravity and the microturbulence difference is also quite small.
Okay.
It is very impressive result from so we obtained these parameters from two independent stars, but they show the same parameters.
Okay.
Yeah,
Okay.
especially for the last one, the SVO 3206 A and B shows almost identical as the parameters. The temperature is same, and the origin and VT is almost similar. This means that they were Fourier twin stars formed together.
Okay. Okay. Yes. Okay.
Yeah. Okay. That's our atmosphere parameter determination. And next step is to measure the chemical abundances using these parameters.
Okay.
Yeah. Let's move on to the next page.
Okay. And we will go down.
Yeah. Okay. Yeah. So yes. Before that, so this would you show you the figure 2?
Yeah, it's the
Figure 2 is our determine the atmosphere parameters in the KL diagram, temperature and the gravity. So the color symbol is our target stars. The pair stars are tied in the dashed line. You can see all the white binary stars. The component stars are tied in closely. Especially the one stars on the that star is
that
SV.
one.
Yeah, that is my favorite target in our.
Very good.
Yeah, actually, with this parameter, okay, let's go back to the main text. So with these atmosphere parameters, we measure the chemical abundances over here. So iron, sodium, magnesium, aluminum, silicon, sulfur, potassium, calcium, titanium, chromium, nickel, and cesium.
And see.
Yeah. At that time, we measured the chemical abundances through the spectral synthesis method using the MOOC.
Yes.
Yeah, MOOC is one of the well-known spectroscopy.
Yes.
Yeah. In addition to these elements, we can also measure the carbon, nitrogen, and oxygen element for one target, SVU3206. So we'll move on to the right panel. Nice color. Yes. Yeah, here. So we can measure the carbon, nitrogen, and oxygen from CO, CN, and OH band.
Okay.
So actually, in the neon paralyzer, there are a bunch of these molecular bands. So we can measure. I think we can measure more precise abundances, these CN abundances. But for other stars, their temperature is relatively high, so we cannot measure these elements with a good conditions. So we didn't measure these elements for other stars.
Yes.
Yeah. So now we measured all elements from these stars, so that the reduction is finished. And let's go to the part of the result.
Okay. All righty. Oh, here's
this is the table of the measured element.
Yeah. Good. Okay. Down we go. And then table 5 is the systematic uncertainty.
Yeah. I can skip this big table because this is kind of the error propagation. Here, in section 4, this is our result of the chemical homogeneity of the white binary system. The first result is for the metallicity, Fe abundances. That is because that is most important element in the stellar physics.
Yes.
Yeah. And when we measure the metallicities of each star, so we can find the very small differences in FeOH between the component stars for all 5 white binary systems. As you can see in this yellow box, the difference is less than 0.01 dex. The largest one is 0.072, and the smallest one is 0.001 and 0.112. This is really tiny differences obtained from 2 different stars.
Yes.
Yeah, and this similar metallicity, this very equivalent metallicity together with proper motion and radial velocity is strong evidence that these two stars were formed together.
Yes, Koival. Yes.
Yeah, and the problem is the fourth one, SVO 2759. Their difference is 0.073, but the difference is not that large. But the problem is from the temperature estimation. So here, the purple box is challenging or the problem of my articles. This is why we using the many kind of the reading map. So actually, for other stars, their reading value is quite small, so less than 0.05, and their reading value is very so similar in many different sources. But in case of this star, it's paired. As we use 2755, they show very large extinction and also large variation depending on the reading source. So when you're using different sources of reading, the metallicity was really different values.
Yeah. Okay. I get it.
I'm gonna show you what is a problem in the next figure. So we move on to the next page. There is some figure. Yeah, here, this figure 3. This figure 3 is the reading value for star SVO 2755. The first one is component A, second, the bottom panel is for the component B stars, and the different color is the different reading source. And the sharp current doesn't provide the distance information that is constant on the green.
Okay.
But other reading source has provided the distance information, and you can see they are changing depending on the distance. And this dotted vertical line is the location of our target stars. And the problem in this our star is just located in front or behind or in middle of this highly obscured region.
Yeah.
So depending on what kind of the reading value when we adapted, this reading is highly changes. So
yes, a lot.
That's a problem. So this is the reason it makes a large differences in FEOVX measurement. So among these many kind of parameter, we finally using the staging value, the blue one, the most bottom one. So
the blue one still is okay.
yeah, blue. Yeah. So because in principle, we expected that these two wide binary systems located nearby and also they form together. This means that they have the similar chemical property. So when you're using this staging value, the difference in metallicity would be minimum. So we think that is more reliable.
Okay, gotcha. I'm with you.
I don't know which one is bad, which one is rare, but
we'll start here. It's a good start, right?
Yeah, right. So we think that it was a good approaches.
Okay.
On the other hand, these results show us that the wider binary system can also be used to check the validity of the extinction map.
Yes.
In this way.
Right. Good.
Okay.
Cool.
Anyway, we are very happy with using these staging values, and yeah, and in this analysis, I'm very happy with that. In these days, the reading map is very accurate, and they provide very useful information depending on the distance. That is very good achievement to our studies.
Yes.
Okay. So now I think we solve why we using the many kind of reading map, and we adapted one value. And the next figure is figure 4 here. So in figure 4 displays the comparison of the spectra in the H band and K band the observation.
Do a global.
This figure is my favorite. Because I like this figure. So this is a spectrum for all of the stars, and so from upward, these two stars, blue, the dark blue and the light blue is the spectrum for component A and component B star. These are obtained from two different stars, but you can see the feature is really similar in this between these stars.
They are.
Yeah, so we also marking some observation line of the iron silicon, but the observation line is also similar, the continuum value is similar, and all the spectral feature is very similar. Not only in H band, but also into K band. So they shows very good agreement in between two component stars.
Good.
Yeah.
Yes.
There is only a tiny differences, and this is strongly demonstrate that the wide binary two component stars of wide binary has very similar chemical properties and very similar whatever, so very similar atmosphere and abundances.
Right.
And
Right.
so this is also highlight that the power and stability of the eigen's near infrared spectroscopy, because we obtained the two spectra from the independent stars and they show quite similarity. This highlight the power of the eigen's.
Yes.
So this is why I like this figure, and this is the main result of our research.
There you go.
Yeah.
I have to admit, this is the figure that made me go, let's talk about this paper.
Yes, right.
So it's
okay.
I think it's a beautiful figure too.
Yeah,
Okay.
thank you.
Yep.
So, okay, so would you move on to the previous page?
Yep. Mm-hmm.
Yeah, okay. So, okay, here, so I already mentioned about the left columns and move on to the right column. So, for the other elemental abundances, we already confirmed that there is the small differences in the metallicity between component stars, and we already measured the other elements, more elements, so we can confirm that from the stars. So for other stars, we also check that we also find these small differences between the two component stars. That is from the 0.05 to 0.09 axis. So would you move on to the figure 6?
Figure 6.
Yeah, it's a 2-page later.
Figure 6, and here, there are our favorite ones, and the ratios. Okay.
Yeah, here figure 6. This is for the other element and the chemical abundances. So two component stars are compared in this row, and the upper panel is the differences, and the lower panel is for the actual abundances. And you can see the difference is quite small for everything, every stars. So this is also in good agreement with that these two component stars form together and evolve together, so evolving in the same procedure.
That's good.
Yeah.
Good.
That definitely shows the chemical homogeneity of wide binary stars from in many abundance plane. Okay, this is our main result, and also it's time to discuss about this result. And the first discussion is the trend with the separation. So would you go back to the previous page again, the 2-page subwork?
1 and 2.
Yeah. Okay. So a slide. One more.
One more.
Yeah. Here, this part. So actually, so we checked some kind of the trend of the abundance differences. Yes, this section 5. Section 5. So at the beginning, here that's enough. Yeah. So there are some formation scenario for the formation of the wide binary, but we don't know yet so which one is rare. But this is difficult. All these formation scenarios successfully explain the chemical homogeneous wide binaries of the wide binaries. So we don't know yet. But so one possibility is the trend of the abundance differences with the separation index, the wide binary separation. So in the next page.
Yes.
So one approach is by the previous paper in the text is to check the difference in abundances, so as a function of the separation. Yeah, here.
Yes.
Yes, the Leo et al. 2021, they say the larger star forming clouds, they claim that the correlation between abundances differences with the separation.
Yes.
So this is because the large star-forming clouds are less homogeneous than smaller clouds. This means that the wider separation of wide binary shows more abundance differences. So it is confirmed from several studies, and from our study, we observed many wide binary systems with the wider separation larger than 10,000 AU. So our data will be definitely help to check that correlation.
Okay.
Yeah, this is listed in the next figure. So
Okay. Two right. Mm-hmm.
so go down. It's actually it's in maybe page 11.
Oh, I'm sorry, I got the wrong figure.
Yeah. So
Which figure?
I gonna skip this figure. Which will go maybe
Figure 6.
figure 8.
8. Okay. 8.
7 here. 7. Sorry.
We'll
Yeah.
get there. We'll get there. I'm with
Okay.
you. All good.
Okay. Thank you. So
Okay.
here the open symbol is the
yes.
data in the
Right.
previous studies, and the color point is our data, and the x-axis is the separation between two component stars, and the y-axis is the difference in metallicity between two component stars. And here, so you can see, and here it is not clear there is a strong correlation between separation and that type of weighting, but it seems that there is some variation. The variation of the that type of weight is increases with the separation, with the increasing separation. So in the wide binary with the large separation shows more variation. But it's kind of rare, but it's not only trend of we can see it from this figure. So when we see this red point, one, they shows moderate differences in FEMT, even though their separation is quite large, 10 to the 5 AU, 100,000 AU.
Right.
So this means that the separation between the two component stars is not the only factor on this. And also we can see the blue one and the purple one, their metallicity differences is quite small. It's almost 0.001 and 0.002, even though they are located, their separation is rather than 10,000 AU.
Right.
This result is very impressive. This means that so in general, the metallicity differences increases with the separation in general, but that is not the only factor. There are more about this. So we think that these two stars, so very tiny metallicity differences with wide separation, they may be formed in the close nearby and then far apart from them. That is more reliable for these stars. So from this figure, we want to say that we need to check individual properties of the wide binary. So maybe the formation mechanism of the wide binary is not one channel. There is multiple channel is possible.
Yes.
That is what I want to say from this figure.
Yes.
Okay, and the next one is so I skip the detail about the figure 8 because this is a similar figure but for the other elements.
Okay.
And we can see the similar trend for that. And the last figure is figure 9, and this is what I want to discuss about the star-planet interaction.
Okay.
Yeah, here. So, okay. So in the introduction part, one of the interesting research we can done with the wide binary is the star-planet interaction. And in this wide exoplanet era, this is very important to study. Yes. So already in many studies, they are checking their planet star interaction. So one method to check that is to see the function of the condensation temperatures. Yes. So we can we can divide the element into volatile and refractory element. Volatile is CNO and the refractory is the others. So volatile element is the main source of the gas giant planet, and why the refractory element is the main source of the terrestrial planet, such as Mars. And if there is some kind of the planet around the stars, so we can see some difference in this probe.
Yes.
This concept came from this. The wide binary stars have very similar properties, and they are far enough to do not interact each other. So if there is some difference in abundance, this could be due to the planet. That is a theory. So already in some study, they show some correlation or anti-correlation in this figure. And this is the evidence of the planet or gas planet or the telescope planet. Okay. So actually in our paper, in this paper, that is not our main goal to study the star-planet interaction. But fortunately, we can measure the carbon, nitrogen, and oxygen abundance for this SVO3206 pair. We can check the validity of this study. Yes. So here, there is no trend. There is no trend. almost flat. So this means that this SVU 3206 A and B have the similar so planetary system. So
Okay.
maybe they don't have any kind of planet both, or they have the same number of the planet both.
Okay. Right.
Yeah. This is just testing test for this kind of study. And so we can see this. We can see that we can do this with this algorithm data. So we will later study about this for some white binaries with known exoplanets.
Cool. Very good.
Yeah.
Very nice.
Okay. It's time for the discussion and the conclusion. And
Okay.
then, okay.
Let's see. Summary and conclusion.
Yeah, here. Summary and conclusion. So, and the first page, I said this, in this article, we had two aspects. The first one is for the wide binary, and second one is for the near-infrared spectroscopy. So
Yes.
for the wide binary point of view, so we find there very nice chemical homogeneity between the components of each wide binary. So their metallicity and the chemical bonding person is quite small in spite of their large separation.
Right.
Yeah. And for the near-infrared spectroscopy, so as I mentioned in the figure for the spectrum, the beautiful spectrum, so we think that our study demonstrated the power and validity of the high resolution near-infrared spectroscopy for the wide binary system study, and also for other galactic stellar study.
Yeah. Very good.
Yeah, that's our conclusion and its future. So we will continue. Yeah, we'll continue our high-resolution spectroscopy for more wide binary system. So actually, at the later time, we will this one, the later page. So we will more focusing on some kind of the peculiar wide binary. So we're planning to observe some wide binary with the planet.
Yes.
And also we want to observe some wide binary. It has the accretion origin related with Gaia and Celadus or Hemi.
Right. Yes. Okay.
Yeah, that's our observing plan in the near future. And actually, some data is already obtained from the previous observing runs. So,
well, we'll come back to that.
yeah, let's see. So, what is interesting from this data?
Yeah. Very good. Very good.
Okay, that's all for this article.
Dongwook, I want to thank you so much for walking us through your very lovely article.
Yes, thank you.
And you mentioned it a couple of times, particularly there at the end on the near future. So let me ask, if we go a little bit longer term in the future, where do you think this goes on that time scale? Are there going to be efforts to, instead of doing 5 wide binaries, to have 50 wide binaries? Things along those lines, and new instruments coming up, that kind of stuff. So where do you think we go in the medium term future?
Yeah, actually, as I think that the Gaia is still operating.
Okay, yes.
They will find them more wide binary, and they will find to report more peculiar system. So, and we need to check that, and from many individual spectroscopic observation or survey observation. So one goal is to check the wide binary and investigate their chemical properties. So we need a lot to do. So after Gaia DR4 or DR5 and still, so lots of things. So with that, the large size of the wide binary, so we can do that. We can do many things with that. So I hope so.
Cool. Very nice. It'll be really fun to see this wide binary develop over the next couple of years. Very nice.
And also for the new instrument and for the near-infrared spectroscopy. So I think the near-infrared spectroscopy is very powerful tool for studying the stellar things. But so far, so mainly the stellar atmosphere and chemical property is studied with optical band. But I think NIR, near-infrared, has very powerful to study their galactic bulge region or cool stars or their exoplanet. So in my personal opinion, I would like to study some stars and stars in global cluster stars or the global cluster in the located in the galactic plane and the galactic bird.
Nice. Very good. Cool. Very cool. Nice. All right. That will do, everyone. And thank you so much. And we will see you on the next one. Bye-bye. And